Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello and welcome everyone. It's a great pleasure to have Matt visit us, and it's an even greater pleasure to have him give a talk because Matt gives wonderful talks.
Thanks.
No pressure, Matt. Matt graduated from MIT last year and has been a postdoc at Princeton since then. And Matt has won many fellowships and awards, including the MSR Graduate Fellowship and the ACM Doctoral Dissertation Award for the wonderful work he's done on algorithmic mechanism design. And Matt will tell us about what he's been working on recently on interpolation mechanisms. So over to you, Matt.
All right, thanks. Okay, thanks for the introduction. And so this talk is going to be on two works. The first one is joint with Nikhil and Jieming, Morgenstern and Vasilis, and the second, which was a follow-up, is with Mark Braverman and Jieming Mao. So the first part of the talk is I'm not going to tell you what interpolation means, and I'll just talk about simple combinatorial auctions. Okay, so just to make sure everyone knows what I'm talking about, in a combinatorial auction, there's a set of m items for sale to n different bidders. And the buyers have combinatorial valuations for the items, so they just have a valuation function that takes as input a set and outputs their value. For this talk, I'm always going to assume that the valuations are subadditive. And the goal of this problem is to find some way to allocate the items that maximizes the welfare, which just sums over every bidder their value for the set they get. And the catch is that these valuations are private information to the bidders, and so they might lie to whatever algorithm you try to use if they think they can get a better outcome. So this problem's been around for a while, and there's kind of three different approaches that we use to solve them. The first is due to seminal works of Vickery, Clark, and Groves. And what they show is that there is always a truthful mechanism that allocates the items optimally. And so by truthful, I mean that this mechanism has a property that every bidder prefers to report their true values to the mechanism no matter what the other buyers choose to do. And kind of the drawback of this solution is that in basically every setting that we care about, it requires exponential computation or communication to actually run the VCG mechanism. So this is basically never used in practice. A second approach that people have used more recently is to say, okay, we can't run the optimal mechanism in practice, but maybe we can design an approximately optimal truthful mechanism. Okay, and there's been a lot of work on this front, and a lot of the approximation ratios that we get are actually quite good. The catch is that these mechanisms are often quite involved, and they're not transparent to the buyers what's going on, and they're also difficult to implement, and so these are also virtually never used in practice. And kind of the drawback of these is that they're not simple in design. Right, so buyers don't like participating in these mechanisms, and sellers don't like implementing them.
What is used in practice?
Sorry?
What is used in practice?
So that's approach 3. So, okay, price of anarchy is not used in practice, but what we often see in practice is people are just using very simple mechanisms that are not truthful. And before this long line of work on price of anarchy, we didn't even really have any understanding of why they should be good in practice or why anyone should want to use them. So what people have started doing recently is we're analyzing simple mechanisms. So for instance, maybe the simplest thing you can think of is just I'll run a second price auction separately for every item, and then bidders, you can do whatever you want. It's not truthful. Okay, and so what the price of anarchy studies is we say, okay, the mechanism's not truthful, so I don't want to try and predict how bidders will behave, but maybe at the very least they'll do something that constitutes some kind of equilibrium behavior. And then we try and prove claims that say, you know what, as long as they play according to this equilibrium behavior, things are not so bad. And so the formal definition of price of anarchy for an auction A searches over all instances, so for all valuation vectors that you want your guarantee to hold, over all possible equilibria, and it finds the worst equilibrium of the worst instance and compares the ratio of the welfare to what you would get in the optimal solution. Okay, and so actually there's been like a ton of work in the last couple years about showing that many simple auction formats have low price of anarchy. In particular, selling every item separately has a low price of anarchy as well. Okay, and recently a critique was raised about all of these results, which is that none of the equilibria at which these price of anarchy bounds are known to hold arise naturally. And I'll be a little bit more formal about what I mean by that later. And in particular, some are even known to be computationally hard to find. So what this means is that, just because we think it makes sense for people to play games at a Nash equilibrium, if it's computationally hard to find, then maybe a price of anarchy bound at a Nash equilibrium that we don't know how to find is not, is not as appealing as for solution concepts that we know how to find. Okay, so what I'll say about these is that these mechanisms are not strategically simple, in the sense that buyers cannot look at these auctions and figure out what they should be doing to play. Okay, so here's just a chart that summarizes what we know so far. So these are the 4 categories that I want to talk about in this talk. So we care about the approximation ratio or the price of anarchy. We want all the mechanisms to run in poly time so that we can actually use them. We want the mechanisms to be strategically simple in the sense that buyers should be able to figure out what they should do. We also want them to be simple in design so that people are willing to implement them. Okay, and so what we know so far is that we don't have any mechanisms that kind of check all the boxes. And what I'm going to show you in the first part of this talk is a new auction format that we call the single bid auction that has a price of anarchy of log m. And it has a poly communication and runtime. It is strategically simple, and I'll be formal about what I mean by that later. And it's also very simple in design. So, okay, so this is like a fuzzy statement. I can't prove that it's simple in design, but I'll describe it to you, and I think you'll agree with me that it is pretty simple.
Why do you say it's not simple in design?
I think it's up for debate. So like it's simple in the sense that I can describe the mechanism to you, right? I mean, you know what it is, but on the other hand, like actually running it, is NP hard to do, so there's going to be some crazy optimization going on, and this is still not something someone is going to want to implement. So I put a question mark there because I don't want to discuss it. Yeah. But even so, even if you think it's simple, you still can't use it in practice.
And also this is like only in one setting, like the auction happens only one shot, right? It's not repeated. Because I think some of these results extend if it is repeated.
So these results, okay, so what they show is that the auctions still have low price of anarchy in the repeated game. The catch is that even what you would naturally say is, oh, in the repeated game, people are going to play no regret learning. It's even computationally infeasible to do learning in these auctions. Okay, so you shouldn't even expect to be able to converge to correlated equilibria, and actually that's relevant to what I'm going to say soon. Does that make sense? So even learning you can't do. Okay, for the other, okay. So this is the first part of the talk. I'm going to describe the single bid auction. Okay, so here's what's going on. In the first phase, each bidder is just going to submit a single bid, so just one real number. In the second phase, the bidders are going to be visited one at a time in decreasing order of their bids. And then when they're visited, they can purchase any number of remaining items they want, and they have to pay their bid per item. Okay, so I have a little animation. Okay, so the first phase, everyone submits a number. So Jieming is bidding 5, Nikhil is bidding 8, and Vasilis is bidding 6. And then in the second phase, Nikhil was the highest bidder, so he goes first. He can buy any of the remaining items that he wants. He chooses the apple, and so he pays 8. Okay, and now Vasilis is the next highest bidder, so he shows up. The apple is already gone. He can buy any subset of the orange and bananas, and he chooses to buy both of them, and he pays 12, which was 6 per item. And now when Jieming comes, there's nothing left, so she gets nothing and pays 0. Okay, so is the format clear? Fair. Okay, so hopefully you agree with me. I think this is pretty simple, too. Okay, so the main theorem we show, and again, these statements are a little bit informal. So first, we showed that the single bid auction has a price of anarchy log m whenever buyers are subadditive. And so the reason this is not formal is because I haven't defined the equilibrium concept yet. And second is that the single bid auction is learnable. So what I mean by that is that whatever regret minimization algorithm you want to use, it will run in poly time. Okay, so what this means is that this single bid auction has a price of anarchy log m. It is a solution concept that you should actually expect to arise in practice. Because in practice, when bidders play repeated games, we expect them to have no regret. Okay, and this says you should expect them to be able to minimize regret because whatever algorithm you expect anyone to use, it will run in poly time. M is the number of items, that's right. Okay, and I just want to, before I go on, recall that all previous auctions either didn't run in poly time to begin with, they were prohibitively complex in design, even though they did run in poly time, or the price of anarchy bounds were only known at unnatural or intractable equilibria. Okay? So are there any questions? I'm going to get into proving some things next.
Just about the last bullet here, so don't need, are there other concepts other than the price of anarchy that would correspond to a different solution concept that will be relevant to these other things?
So another thing people study is the price of stability. And we do know that price of stability is looking for the best equilibrium. And we do know not for subadditive buyers, but for subcases, we do know how to find at least one equilibrium efficiently. And we know how to find an equilibrium that has good welfare. The problem is that these equilibria are extremely unnatural. It's basically like one person bids something very high and everyone else bids 0. And it looks like this on every item. And it requires a big centralized computation to find out what's going on. So technically, there are pure Nash that exist for some of these simple auction formats that have good price of anarchy that we know how to find. But they're really unnatural, and I don't think you should expect to see them in practice. But that's the extent of what I know of other approaches.
So sorry, just to understand this price of anarchy bound, which it depends on the auction.
Yes. So every auction has a different price of anarchy.
Which is you look at a set of equilibrium that can be reached with this thing.
Yes. So for every auction, for every class of valuations, you look at what is the worst instance. For that instance, find the worst equilibrium, and then see what is the ratio of what I would hope to get versus what I get in this bad equilibrium. So it's defined for an auction and for a class of instances that you want to have a good bound for.
Notion of
And for whatever notion of equilibrium you want.
And even the approximate equilibriums are hard to complete.
Even so, we don't have formal results saying that approximate equilibria. So I think the approximate is like really, really small, like exponentially small epsilon is hard to compute. I don't even think we know that like p-test doesn't exist or something. But like a meta argument, I would say, look, if you're using a complex p-task just to find an equilibrium, I don't know that you should expect bidders to do that in practice either. Yeah. Okay, so there's kind of two separate claims going on here. The first is just talking about the price of anarchy. The second is just talking about how well bidders can learn this auction. So the price of anarchy, so there's been this recent development of techniques called smoothness that have kind of like become a big hit in price of anarchy recently. And so we're again going to use these same techniques. I'll explain them starting from scratch. And that's going to be the majority of the first portion of the talk. And it turns out it's actually pretty straightforward to show that this mechanism is learnable. And basically what we're going to show is that when a bidder is trying to do learning, they only need to consider a polynomial number of actions. And when there's a polynomial number of actions, however you decide to learn, it's going to run in poly time. Okay. So I'll get started with smoothness. So what smoothness is, it's a generic tool for proving price of anarchy bounds at many equilibrium concepts at once. And so here's the formal definition. I'll parse through it in a second. But we say that a mechanism is lambda mu smooth if, for every valuation profile that you're hoping for your bound to hold, each bidder has some safe strategy. And this safe strategy should satisfy the following guarantee. So what this is saying, on the left-hand side, we're summing over every buyer their utility for deviating to their safe strategy from the existing profile. And then on the right-hand side, this is just lambda times the optimal welfare and mu times the optimal revenue. So this right-hand side is just a bound, and you say, look, if everyone has a safe strategy such that the sum of utilities deviating to the safe strategy exceeds some bound, then something nice happens. Okay, and there's something nice that happens is Syrgkanis and Tardos showed that whenever a mechanism is lambda mu smooth, then M has a price of anarchy of at most this bound, so this is just mu over lambda, at basically every equilibrium concept that you would care about. Okay, and I'm not going to prove this because this is older work, but basically the idea is that how you reason is that if you have a strategy profile that's any of these equilibria concepts, every buyer is at least as happy in this equilibrium as they would be by deviating to their safe strategy. Okay, and so this means that the sum of everyone's utility is at least as large as this term on the left, and then the rest of the proof is just moving around terms from this inequality. Okay?
The UI is
Where? Okay. Yeah, yes, that's right. Yeah. So this should be what's on the left-hand side. Okay, so let me give you an example first of how you might show that a mechanism is smooth, and then kind of relate this to how you should understand why this implies a price of anarchy bound. So let's say that there's one item for sale, and we're going to run a first price auction. So Syrgkanis and Tardos also showed that the first price auction is 1/2 smooth, and therefore, by their previous theorem, the first price auction is price of anarchy at most 2 at all of these equilibrium concepts. Okay, so let's see how you would prove this. So for each bidder, we have to define their safe strategy. And their safe strategy is going to be to bid half their value. Okay, and now for whatever strategy profile we're looking at, let's let P be the probability that the highest bid you see in this strategy profile exceeds the highest value over 2. Okay, and so what's going on is that whenever the highest bid is larger than the highest value over 2, certainly the revenue is at least the highest value over 2 as well. So the revenue is at least P times opt over 2. And also, whenever the highest bid is less than the highest value over 2, now the highest bidder will win the item when he uses his safe strategy. And when this happens, he only pays half his value, so he gets utility half of his value. Okay, so this means that just by the highest bidder, his utility by deviating to the safe strategy is at least 1 minus P times opt over 2. And now when we plug both of these back into this bound, we'll see that you can get lambda equals 1/2 and mu equals 1. Okay, so I think following through this reasoning formally is not super important. But the important thing is that you kind of see how you would reason about this. Okay, so every bidder has a safe strategy. And by reasoning through what happens, we can see that everyone's utility exceeds this bound. Okay, so how I think of interpreting this is that in any of these equilibria, the highest value player is at least as happy with whatever strategy he's using than he would be if he used his safe strategy and just bid half his value instead. And it turns out that this fact alone means that the price of anarchy is at most 2 at these equilibrium concepts. Okay, and the way you prove it formally is going through smoothness, but intuitively this is what's going on. Okay, so any questions? Okay. Okay, so now I want to do a slightly more complex example. So in the single bid auction, I want to only look at very simple valuation functions and show that the single bid auction has a low price of anarchy here as well. So I'll define this constraint homogeneous and call it CHV. So a valuation is constraint homogeneous if there exists a set S and a value X such that your value for any set is just X times the number of items in S that you get. So you're additive, except your value for every item is either 0 or X. So it's a very restricted class of valuations. Okay, and so something we show is that the single bid auction is also 1/1/2 smooth whenever buyers are constraint homogeneous. And I'm not going to go through a complete proof, but, oh, sorry. This is just reminding you of what the single bid auction is in case you didn't remember from the earlier slide. So there's this phase 1 where everyone submits a single bid. In phase 2 where the bidders are visited one at a time and they can buy whatever set of items they want. And so the proof idea is the safe strategy is going to be basically the same as in the first price auction. Every bidder's safe strategy is going to be to bid half of their per item value over 2. And then when they get visited in the second phase, they're going to buy whatever items in their special set remain. Okay, and then the rest of the proof I'm going to skip, but it's very similar to the smoothness proof for first price auctions. You're just summing a different bound over each item. Okay. And again, how you should interpret this is that in any equilibrium, every bidder is at least as happy with the strategy they're using as if they deviated to their safe strategy instead. And in this case, their safe strategy is bidding half their per item value and taking whatever items are left in phase 2. And this fact alone implies that the price of anarchy is at most 2, and the formal way you show this is through the smoothness. Okay. So what do we see so far? So proving that single-dimensional auctions are smooth is not so bad, but directly handling combinatorial valuations is much harder. And kind of the reason is that we can't break down per item contribution on when we try to prove these bounds because the valuations are combinatorial and they're weird. Okay, so what we would like to do is come up with some kind of lemma that will let us reduce proving smoothness bounds for complex valuations to proving smoothness bounds for simpler valuations, which you can see is not so bad. Okay, and so it turns out that the right notion that we need is this definition that we'll call a pointwise B approximation. So say that a class of valuations, V, big V, pointwise B approximates big V prime if for every valuation in V prime and subsets S of items, there exists a little v such that this first guarantee is just saying that little v is close to V prime, at least just on this special set X. And the second claim is just saying that V lower bounds V prime everywhere. Okay, so this is a really weak notion of approximation. The only guarantee is that V and V prime are close on S. Everywhere else, V could be like 0. It could be infinitely smaller than V prime. We don't care, as long as it's less than V prime. Okay. So what we show is that even this really weak notion of approximation suffices to get this kind of extension lemma. So the claim is that whenever a class of valuations, pointwise B approximates another class, and you have a mechanism that's lambda mu smooth whenever valuations are in the simpler class, then M is also lambda over B mu smooth for this more complex class. Okay, and the proof, it turns out, is actually not so hard. It just uses each of these properties exactly once. But I'm not going to go through it because it's mostly just chasing around these inequalities. Okay, so now the interesting thing that we show, and this is a little bit more technical, so I'm omitting this as well, is that constrained homogeneous valuations, pointwise log m approximates subadditive valuations. Okay, so this means that for every subadditive function, for every subadditive function and for every set S, there is a constrained homogeneous valuation such that, I lost the definition. Oh no, it's up here. Such that it's close to that subadditive function on S, and for everywhere else, it's no larger. Okay? And then this alone by our theorem says that the single bid auction is now 1 minus 1 over e log m1 smooth for subadditive bidders. And this is using the fact that it was smooth for constrained homogeneous and this extension lemma. Okay, so therefore what this means is that the price of anarchy at all these equilibrium concepts is at most 1 minus 1 over e times log m. Okay. And again, so how you should interpret this, stepping back from the smoothness and how the proof comes, is that in any equilibrium of the single bid auction for subadditive buyers, every bidder is at least as happy with their current strategy as they would be if they use their safe strategy. And what is their safe strategy? It's to pretend they're constrained homogeneous, bid half of their per item value, and then take whatever items are left in their constrained homogeneous set. Okay, and then this fact alone guarantees that the price of anarchy is at most 1 minus 1 over e log m. So I want to point out too that this guarantee holds even if the bidders don't know what their safe strategy is. Okay, so the point is you might look at this and think like, okay, maybe I don't know what CHV valuation I'm supposed to pretend I am, and that's reasonable, but what an equilibrium guarantees you is that whatever your safe strategy is, you prefer to do what you're doing than anything else. So you don't need to know what this special anything else is. You prefer to do what you're already doing than to deviate to it.
So sorry, what's the concept of equilibrium over here?
So So where is it? Any of these. So Nash, correlated, coarse correlated, or Bayes-Nash. And I haven't defined them yet because it's not going to be super relevant yet. Okay. Okay, so this is the first part of the theorem where we show that the single bid auction is 1 minus 1 over e log m smooth for subadditive bidders. And therefore, the price of anarchy at all these equilibrium concepts is at most 1 minus 1 over e times log m.
Does this mean anything about the price of anarchy at approximate equilibria?
So specifically when you do a smoothness proof, it also extends to, so if you have like a epsilon coarse correlated equilibrium, you just lose multiplicative epsilon here. Multiplicative, it's 1 minus epsilon times this bound. This is not necessarily true for any price of anarchy bound, but specifically ones that are proved through smoothness. They're also smooth with respect to approximate concepts. Okay, so the next thing I have to do is, so I told you that the important part about this auction was that some equilibrium concept at which this bound holds should arise naturally. Okay, and it's going to be coarse correlated equilibria. Okay, so let me put these two theorems on the board that maybe you're already familiar with. So the first one is just relating learning algorithms to coarse correlated equilibria. And so what this says is that if you have any game, and that game is played multiple times, so think every round you play the same game, if every player plays a strategy that guarantees no regret, then the aggregate strategies that randomly sample a round and each player plays their strategy from that round converges to a coarse correlated equilibrium. Okay, and I'm actually still not going to formally define what a coarse correlated equilibrium is. The only thing that's important is that every player separately minimizing regret converges to a coarse correlated equilibrium, and the price of anarchy bound that we proved holds at this equilibrium concept. Okay, and then another theorem is if a player is trying to do no regret learning and there are k possible actions that they can take, it is possible for them to do this in time and space poly in the number of actions. Okay, and by no regret I just mean that, because this is a standard definition, but every player is happier with the choices that they've made than playing any fixed action every round. Okay? So let me just give you some examples so that we can see why you can't do no regret learning in some of these other auction formats.
Question about the significance of the first theorem.
Yes.
So you say that the players can learn in equilibria, but in each round of the learning process itself, they are not necessarily in equilibrium.
That's correct. So that's correct.
They need to switch eventually to.
So it's not quite like that. So what's going on is that so formally the reason that you care about price of anarchy bounds at coarse correlated equilibrium, even though every day they're not necessarily playing one, is that if you look at the average welfare across every day that the game is played, this is saying that the average welfare is necessarily good because the strategies that are played over time is an approximate coarse correlated equilibrium. So it is not the case that any single day you can look and say the welfare is good on this day, but you can guarantee that over time the average welfare is good.
So because every day maybe.
So
Just saying.
what is coarse correlated equilibrium is if you look at the empirical distribution of plays, you pick one day at random, then everybody plays the corresponding strategy. That is a correlate. So then the welfare rate is corresponds to the average welfare.
Yeah.
Okay. So it's not the same as cohort. Okay, the course means that you can just pick a day at random and have everybody play the strategy for that particular day.
Yes, that's right. Yeah. So does this make sense? So the important thing is that over time, the average welfare is guaranteed to be good because of this claim. Okay. So as an example, let's say that we decided to use the simultaneous first price auctions format, which is known to have a price of anarchy of 2. So each bidder has exponentially many possible actions in this mechanism because they can place a different bid for each of the m possible items. So if they can place at least 2 different bids for each item, then there's 2 to the m different strategies. So they can't necessarily in polytime run no regret learning. Okay, so this isn't a proof that you can't do it, but at least you can't just use an off-the-shelf no regret algorithm, and maybe you shouldn't expect bidders to be able to do this on their own. Okay, in a sequential first price auction, it's actually even worse. Each bidder has exponentially many in nm, number of bidders times number of items, possible actions, because now they have to consider what are they going to do for every possible history of bids on the preceding items. Okay, and so maybe this is a little bit more interesting, is that if instead you have a truthful auction, then each bidder may have many possible actions, but they can always guarantee no regret just by telling the truth every round, right? Because we know that every round, no matter what happens, you're happier telling the truth than doing anything else. So you only have one possible strategy that you need to consider, okay? This last claim is important. Does that make sense? So even though you may have lots of actions, you only need to consider one of them. Okay, so here's an observation about the single bid auction, is that during phase 2, when the bidder is visited, and there's some set S of items that remain, they have no incentive to select anything except for their favorite set that they can get, right? So they can't affect anything that happens to them in the future. They can't affect any other bidder's behavior. So they might as well, at this point, just pick their favorite set, which will maximize their value for that set minus what they have to pay to get it. So what this means is that even though the bidders technically have exponentially many strategies during phase 2, they can always minimize regret by just picking the best one. So they don't need to learn what they should do during phase 2. Okay, now during phase 1, they just have to submit a single real number. And it turns out that you only need to consider bids that are powers of 2. And this is not an interesting proof. But what this means is that now the only actions that bidders need to consider are actions that during phase 1 submits a bid that's a power of 2, and during phase 2 buys their favorite set of whatever's available to them. And these are the only actions that they need to learn over. And then the punchline is that there's only polynomially many such actions. Okay, so what this means is that because there's not too many actions, however they wind up doing their no regret learning, it will run in polytime. Okay, so this is wrapping up this portion of the talk. So what we showed is that the single bid auction has price of anarchy log m at coarse correlated equilibria whenever buyers are subadditive. And we showed that it's learnable and that any standard regret minimization algorithm runs in polytime because bidders only need to consider polynomially many actions. And spiritually what this means is that it has a low price of anarchy at a solution concept that is actually likely to arise in practice. And just to remind you of how this contrasts with previous work, is that prior mechanisms either were not used because they had prohibitive runtime or prohibitive complex design, or they are used but we don't understand what will actually happen when bidders play them. Should ask Nikhil. I don't know.
So similar versions have been used in some cases. We had an earlier version called draft auctions. This is a repeated version of this. And, that has been used in a few cases. Hopefully, with this, people pay attention to this and use it.
Yeah.
Repeated
And also-
version. How is it related to this one? Is it
So
static
they,
errors or whatever?
so the price of anarchy bonds are the same, but you don't get this learnability.
Yeah, so
Submit a bid repeatedly.
the point is in the draft auctions, how you act the first time you bid may affect how bid, like there's a lot of interaction going on between your first bid, your second bid, your third bid. So it's not necessarily the case that you always want to pick your favorite set of items that's left. Whereas in this one, because it's so short, you immediately want to just pick your favorite thing. Okay, so let me say, so maybe this auction, I don't know, so it sounds like it might be used in practice, even if it's not. What might be more likely to be used in practice is one that fills in this last column. So I think what would be nice, price of anarchy of log m is not bad, but it's also not constant. And we know that the price of anarchy could be 2 for these auctions that don't have, or that we don't know have learnable equilibrium yet. So this, I think, following this work is kind of the main open question, is to find a mechanism that is simple in design, is learnable, it runs in polytime, but has a better price of anarchy.
For the auction you described, the log m is the lower bound?
Yes, so that's the second part of the talk is going to prove that too. It's log m over log m, but log m I think is probably the right answer.
So what is this auction which gets 2?
This one? So this is every item, you just run a first price auction separately.
Not strategically simple. What does it mean to be?
Oh, so it means that we don't know how to find any equilibria of this auction in polytime.
It's hard. Proving.
Maybe spiritually, to think of it, if I told you that you were going to play in this auction, like what would you do? That's hard. Yeah, whereas...
Criticism of natural.
Sorry?
For many games, you can't compute natural.
Yes, that's also true. Yeah, so it's
perhaps you can't learn, that's the main problem.
Yes, so I think that's the big thing, is that you can't even learn, right? So the point is there's exponentially many different bids you could make. So even if you were willing to do some kind of no regret learning, you can't do it in polytime. Whereas for this auction, okay, it's still not obvious to me, like in one step what I should do in a single bid auction, but at the very least, if I run a no regret algorithm, I can do it in polytime and I'll learn something that guarantees me no regret.
What's the polynomial there? It might be...
Which polynomial?
So in your auction, like you have polynomially many options.
Mm-hmm.
So it's like just swap and how many strategies you player has?
So it'll be not, basically it's just how finely do you have to discretize the bid space. So but it's not very fine. So it'll really be maybe like on the order of m or something. Like even if you let them have m different strategies, that lets you send exponentially, like from 1 to 2 to the m, you can represent a lot of values like this. So it may even be less.
Sorry, so let me just try to understand. So in this, you're saying if your auction is that every item goes separately, right? And I bid for every item.
Yeah.
Doesn't matter what, and the theorem will do is that doesn't matter what equilibrium we land up with,
Yes.
it will be within factor 2.
Correct.
The only problem is we don't know how to land up at equilibrium.
That's correct. And in some sense, you should maybe not expect bidders to naturally wind up at 1 magically either, right? Yeah. Okay. So that's so I would say another approach is maybe you could look at simultaneous single item auctions, define a new equilibrium concept and say, I think bidders will do this, and if it makes sense, and then prove price of anarchy bounds there, but we don't know how to do that yet. Yeah. Okay, so the second part of the talk is going to discuss these things that we call interpolation mechanisms, and basically they're going to address, I'll say here what they're going to address is that, so after this got out a bit, so I think a lot of people were asking questions like, oh, there are so many natural generalizations of this auction. Maybe one of these simple modifications will let you significantly improve the price of anarchy. Okay, so, the important thing is you want to maintain that the auction is learnable. So that's a key property. And so a lot of natural ideas are like, okay, bidders could learn over 2 bids instead of just 1 bid made at the same time. This isn't that much more information. Maybe this helps a lot. Maybe you can set a different price for each item. So there's no reason that you have to use the same price for every item. You could report some information and then somehow I come up with a non-uniform pricing. Maybe just subadditive is hard, but it would be nice if this auction worked for submodular or budgeted additive or some other valuation class that was not quite so general. Another thing is maybe we could study the price of stability instead of the price of anarchy. And also I think we just wanted to understand like what are mechanisms like this? So like what should that mean? And so what we did in this follow-up work is we defined a class of mechanisms like this that we call interpolation mechanisms. And using this, we showed that none of these 4 relaxations above can improve the approximation ratio. So if we want to beat log m, we have to do something new. No combination of them, yeah. Okay, so let's define. So an interpolation mechanism, we say, is a 2-phase mechanism. The first phase is just some arbitrary communication protocol. The output of that protocol is a truthful mechanism. Okay, and then phase 2 is just bidders play whatever truthful mechanism was selected during phase 1. So think of the single bid auction. Phase 1 is everyone submits a bid, and the output for phase 2 is a truthful mechanism that visits bidders one at a time, and when they're visited, they are faced with an item pricing that depends on how everyone bid during phase 1. Okay, so does this make sense? So once phase 1 is fixed and in the books, phase 2 is a truthful mechanism. And that's for the same reason that once they get visited, they just want to pick their favorite set. Okay, so I think this is the right way to kind of generalize this format. And again, so what we're interested in is how much time or space does it take to run a no-regret algorithm on an interpolation mechanism. And the point is that, like we said before, bidders will never regret telling the truth during phase 2. So a priori, they just need to consider all possible actions during phase 1 combined with telling the truth during phase 2. Okay, so the important features of an interpolation mechanism will be how much communication and how many rounds take place during phase 1. And this is important because this tells you how many number of actions the bidders are going to a priori consider. And second is what kind of truthful mechanism shows up in phase 2. And I'll use this terminology, M interpolation mechanism, to be if the phase 2 mechanisms come from some class M. Okay, so this definition makes sense? Good. Okay. Okay, and so this is the last definition I think I'm going to give. So we'll say that an interpolation mechanism is a priori learnable if the first phase consists of a single simultaneous broadcast round of communication, and each bidder communicates only log m bits. Okay, so the reason this is useful is because this implies that every bidder only has polynomially many actions to consider in the first round. So they can run any no-regret strategy that they want in poly time. And you can see this is a sufficient but not necessary condition that a learning algorithm exists. Okay. So again, using the single bid mechanism as an example, in phase 1, there's log m communication per bidder, and there's one round, and that's why there's polynomially many actions. In phase 2, I'll call this format a single posted price mechanism. Okay, it picks some prices ahead of time, visits buyers one at a time, and offers them any remaining items at whatever their price is per item. Okay, so, all right. So another view of single bid mechanisms, now that we're looking at it like this, is that this phase 1 by itself is really pretty useless, right? So each bidder is only submitting log m bits, right, when their valuation is a subadditive function, which takes doubly exponentially many bits to represent. Okay, but somehow this isn't, right, so this is not enough to guarantee any non-trivial approximation. The second phase by itself is also completely useless because no single posted price mechanism can possibly guarantee, and it's even worse, you can't get any kind of approximation just using one of these mechanisms by themselves. But interestingly, combining them in the right way somehow results in a pretty non-trivial approximation starting from these two pretty useless components. Okay, so there's some hope that maybe starting with a more useful component in phase 2 will actually let you do better. Okay, and so the right questions to ask for here are how much phase 1 communication does it take in order to get a certain approximation ratio with an M interpolation mechanism? And you can ask this for any class of truthful mechanisms. And what is the best approximation guarantee that you can get of an a priori learnable M interpolation mechanism? Okay, so let's specialize that to the single posted price mechanisms. So how much phase 1 communication is required to guarantee better than a log m approximation with a single posted price mechanism? So how much communication do you need to beat the single bid auction? And so actually, it turns out that no amount of communication, so no single posted price interpolation mechanism, can beat a little o of log m over log m approximation, no matter how much communication happens during phase 1. And this is even when the bidders are just additive. So the buyers don't have to be very complex for this lower bound to kick in. So in particular, what this means is that the best approximation guarantee of an a priori learnable single posted price mechanism is somewhere between omega of log m over log m and O of log m. Okay, so I'm going to give a proof overview of this now. So what we want to do is we're just going to construct an example where no single posted price mechanism does well. And then if we have an example like this, no amount of communication is going to help you magically find the single posted price mechanism that doesn't exist. Okay, so here's what the example is going to look like. There's going to be, for each buyer, there's a different bucket of items. And the buckets are going to have, wildly different number of items. So it'll be n to the I for bucket I. Each item is going to be special for exactly one bidder. And each bidder is going to have a 1 over n fraction of all the items in each bucket is special for them. And bidders value their special items in each bucket at a factor of n more than their non-special items. Okay, so maybe the concrete example is more useful here. So the red items, each different color is a different bucket. So in the red bucket, there's 3 items. Everyone values their special item at 27 and their non-special items at 9. In the blue bucket, there are 9 items. Everyone has 3 special items that they each value at 9, and they value their non-special items at 3. And then in the green bucket, there's 27 items, and they value their 9 special ones at 3 and their non-special ones at 1. Okay? Okay, so clearly the optimal thing to do is just to give every bidder their special item. And now the question is, how well can you do with a single posted price mechanism? Okay, so the trade-off here is that if I want bidder 1 to get his special item in the blue bucket, I have to set a price for him of 9 or lower. But if I set a price for him of 9 or lower, he's also going to steal the special items that I wanted to go to one of the later bidders. And if I want him to get his special item in the green bucket, I have to set a price as low as 3, and then he's going to steal all the previous special items as well. Okay, so this is kind of the trade-off, is that you can't give the first bidder all of their special items without him also stealing special items from the bidders who come after him. Okay, and it turns out that the way the math works out, that opt is n to the n plus 1. No SPP can do better than order n to the n. There are n to the n items in the example, so n is log m over log m. So that's where the gap comes from. Okay, so what this means is that the single bid auction already reaches the limit of the single posted price interpolation mechanisms. What about a more general posted price scheme? So I think the natural next step is we'll consider.
Yeah. Make sure that I understand the intuition. So let's say in that example that you gave before, that if you do your auction, like the first bidder for some reason would announce 10 and the second would announce 4 and so on, then you'd go in the right order and give each one the items that they want, no?
No. So these are the items and these are the bidders. So if bidder 1 announces 10, he would show up and he would buy only red item 1. He would not buy any of the blue or any of the green items. And then he would be gone and he would never come back. And then 2 would show up, and if he bid 4, he would take, so what's left? He would take all of the remaining red items, and he would take his special blue item, but he would not take any of the green items. And then 3 would come up, and let's say they bid 1, they would just take all of the remaining items, whatever's left. Does that make sense? So the point is that, so bidder 1's bid was too high for him to possibly get his special items in the lower buckets. Bidder 2's bid was too high for him to get his special item here. It was also too low for him to pass up on taking 3's special item in the red bucket. So the point is just that every bidder has a wildly different value for the different items, and one number is just not enough for them to represent their preferences, and what you lose is exactly log m. Did that
I think so.
Okay. Okay. So a slightly more general scheme that we want to consider I'll call non-adaptive posted price mechanisms. So here you order the bidders however you like, maybe at random. And then for each bidder and each item, you set a price, maybe at random. And then you visit bidders one at a time and offer bidder I the opportunity to buy any set of items, paying Pij for item j. Okay, so this generalizes it in the sense that now you can have whatever price you want for each item. They can be different across bidders, they can be different across items. Okay, so now it's always the case that there is a non-adaptive posted price mechanism that results in any allocation you want. And for any allocation that you want to induce, you can just set the price of item j equal to 0 if you want bidder I to take that item, and infinity if you don't want them to take that item. Okay, so we're not going to get a strong impossibility result like on the previous slide, because there's always a non-adaptive posted price that results in the optimal allocation. So the question now is, how much phase 1 communication do you need to find a good non-adaptive posted price mechanism? Okay, so just because one exists doesn't mean you can find it easily. Okay, and so the answer is that any non-adaptive posted price interpolation mechanism that guarantees little o of log m over log m approximation still just on all instances of additive bidders, necessarily has at least m to the 1 minus epsilon first round communication per bidder, and this is for any epsilon. This is not just for one fixed epsilon, for any epsilon this has to hold. Okay, and so the proof, I'm not going to go through the proof. It looks similar to the previous construction. The idea is that now we need a family of examples such that no single non-adaptive posted price does well except on an exponentially small fraction. It turns out that using a probabilistic construction and ideas from the previous one, we can do this. Okay, so what this means is that the best approximation guarantee of an a priori learnable non-adaptive posted price interpolation mechanism is somewhere between omega of log m over log m and order log m. Okay, so this means that even for this way more general class of mechanisms, single bit auctions have already reached the limits of these. So maybe what about other classes of mechanisms?
So all of these are additive, right? For additive, we know things should be good, right?
So no, so even for additive, so the problem is that if you have an additive buyer, it takes basically m log m bits to describe your valuation. So if I let you use m log m bits, you could tell me your value, I could allocate the items optimally, there's no problem. It turns out that in order to do anything better than log m over log m, you need basically to say your whole valuation. And that if you use anything less, you can't beat log m, but that just one number is enough to get you log m.
So m log m bits is just around a separate auction for each item.
Yes, so for additive buyers, that's exactly what you would do. Yeah. Okay, so I'm going to just maybe briefly go through this. So we consider two more classes of mechanisms that have been previously studied. I won't read through the definitions, but they're called maximal and range or value query. And very strong lower bounds are known against both of these classes of mechanisms as truthful mechanisms without interpolation. And what we show is that all of the existing lower bounds also extend to interpolation mechanisms that have sub-exponential first phase communication. Okay, so that means these are also not going to let you do anything interesting with a priori learnable mechanisms. Okay, so now I'm going to wrap up. So just to recap, the motivation was we wanted combinatorial auctions that were either approximately optimal or had a low price of anarchy. And we wanted them to be simple in design and also strategically simple. And specifically, we mean learnable. So in the first part of the talk, we showed you the single bid auction. And it's the first one that hits all three of these criteria, but the price of anarchy was still logarithmic and not constant. And in the second part of the talk, we introduced this notion of an interpolation mechanism to try and properly generalize this format. And the way to think about this is it's kind of like mixing a non-truthful and a truthful mechanism. The first phase is non-truthful, but really limited, and the second phase is a truthful mechanism. Okay, and so we prove lower bounds on mechanisms that are like the single bid auction. We show that we've already reached the limits of interpolation with all these classes of mechanisms. The one that we left open is called adaptive posted price mechanisms. So these are posted price mechanisms where, based on what you see for the first couple bidders, you can update the prices of the remaining bidders. So these are, oops. All right, so these are more general than the so that's why I called non-adaptive, the ones that we saw so far, where the prices were fixed. Where the prices were fixed ahead of time. Okay, and we know that the techniques that we have right now cannot possibly prove lower bounds for additive buyers and not adaptive posted price mechanisms. So we need either new techniques for lower bounds, or maybe this is a nice direction for positive design. Okay, and then just to give you this chart one more time, so the left-hand side is what we already knew. The green column is what we contributed with the single bid auction, and then the right-hand column is, I think, a nice open direction, and interpolation mechanisms are maybe a nice way to address it. Okay, so that's all I have. Thanks a lot for listening.
Any more questions?
Did you look at like characterizing the strategy that neuroregret learning would converge to in the single bid auction?
That's a good question. No, we didn't. Yeah, so I guess first you would have to, for different valuation functions, you could test and see what happens. But we didn't look at that. That's actually a pretty good question.
So, but for additive bias, the simultaneous single item
Yes,
auction,
it's optimal. So for additive
it's also
bias,
learnable, right?
it's better than learnable. It's truthful. For additive buyers, simultaneous auctions, you should always bid your value on every item. There's nothing better you can hope to do. Right. So for additive buyers, VCG and simultaneous and sequential they're all the same thing, and they all collapse to good news. Okay. So the reason we were using additive buyers for lower bounds is basically to rule out, you might say, look, subadditive functions are really complex. Maybe you can have a good price of anarchy for some modular buyers or something way simpler. We're saying there's no way that restriction is going to help you, because whatever restriction you come up with, it should at least contain additive buyers. Yeah. So just say, I'm not motivating that searching for better mechanisms for additive buyers is not an interesting research direction. But if you have lower bounds for additive buyers, you shouldn't hope to get anything interesting beyond that.
All right. Yeah. So Matt is here till Monday, and I encourage all of you to talk to him. It's not related to this, or anything else. So it's time.
All right. Thanks.